Hello, this is again Cookie Dive, and the chapter is random variable of the stats and probabilities refresher. A random variable conceptually is a mapping of events to real numbers. So think of an example with a single coin toss, right? So we toss a coin, and if it's tails, then we'll say it's 0. If it heads, it's 1. So you could imagine some sort of a gamble where maybe if it's tails you get nothing, and if it's heads you get $1 or 1 cent or 1 lira, whatever. The idea here is that we're mapping some events, whether the coin coin fell on with tails up or heads up. It's an event. Then we map the event to a real number. So a random variable as such will have a set of possible outcomes, and these will be real numbers in a general case. So 0 and 1 are real numbers. Obviously there's all kinds of numbers in between, and less than 0 and more than 1. But these would be the examples of categorical or discrete random variables. So another example is 2 coin toss. So imagine we toss 2 coins. So in this case you can look at it as if there were 2 events, right? One coin and another coin, and then we create a set from these 2 events. Or you can look at 2 coins if we're tossing them together as one event. So in this case we are saying for instance that 2 tails are mapped to 2, and if it was 2 heads it would have been 1, and otherwise, which means heads tails or tails heads, it's 0. And as you can see with coins, we certainly see 4 possible combinations: tails tails, heads heads, and then we have heads tails, tails heads, 4 combinations. But here we're mapping them only to 3 real numbers, 3 possible outcomes, you see. So the idea that you don't need to map event to a number, event by event. You can map sets of events. So in this case, again, outcomes are 0, 1, and 2. So the understanding of an outcome is very important. In the next few slides, I will point to a difference between an outcome and an observation, right? So in this case, we're talking about possible outcomes. So what can we see with 2 coins toss? We can see only 4 possible outcomes, but they're again mapped to only 3 numbers. So in terms of the random variable, there's only 3 outcomes. In terms of the events, yes, there's 4 events, but in terms of the random variable, which we created in example 2, there's only 3 outcomes. Random variables are associated with probability distributions. So when we are observing some random variable, we say it's coming from a probability distribution. The probability distribution, sometimes called cumulative distribution function or distribution function, or rather I would say probability distribution can be characterized by its distribution function. So if you're just saying distribution function, then it means usually it means the CDF, so cumulative distribution function. So let's think about what is cumulative distribution function. It is as it says, a function. So you can think of any function, mathematical function. So it's in that regard, it is like any other mathematical function, but it has certain properties. So usually we denote it with a capital F. So we'll say f of x, and a note on notation. When we use capital letters like x, so in this context we usually mean the variable itself, all possible outcomes, and when we put small capital X, we mean a particular number. So in this case we will say that f of x, this capital F of x, is a cumulative distribution function, and its value is the probability that our variable x, random variable, is less than a given or a chosen value x. small capital X, right? So it can be a little confusing, but you will get useful. So immediately from this definition, we can see that the probability that our random number is between A and B is the CDF of B minus CDF of A, right? Because CDF of B means the probability that our random variable is below B, and CDF of A means it's below A. So if we are looking at the probability that the number is between A and B, then it must be that it's F of B minus F of A. So the CDF often, not often, but it can be drawn, right, as it can be shown as a graphical representation. So in this case, I believe this is a CDF, the chart which I'm showing on this slide is a CDF of normal, standard normal distribution, or rather normal distribution. Right, so in this case we see that the red line would be for mu 0 sigma variance 1, so that is a standard normal distribution. So we can immediately see that CDF is bounded between 0 and 1 and it's monotonic. If you think of it carefully, you will see that CDF cannot go down. It can only go up or stay the same, right? So that's why we call it monotonic. Right, so it's monotonically increasing between 0 and 1. So the CDF of minus infinity is 0 and CDF of plus infinity is 1. And because as we said, random variables are mapped to all real numbers. So it means into the CDF you can plug any number, any real number. We will see that this interpretation has its quirks when we deal with discrete numbers, but for a second just think of a continuous number which can take any value, right? But here when we talk about the single coin toss, if we have just a single coin toss like we discussed before, with probability of, well, we know if it's a fair coin, the coin is always going to be probability 1.5, right? That it's tails or heads. So in this case, if we draw the CDF of the discrete probability function, right? The discrete random variable, which can take only discrete values, then it turns out this CDF will be a step function. It won't be this smooth function. It will just like it will suddenly jump, right, by a certain value. So let's talk about the difference between discrete and continuous random variables. So possible outcomes of random variable can be discrete or continuous. And if you think of an example of a continuous random variable, then maybe percentage annual return of your stock portfolio could be 1, right? So it can take conceptual, at least it can take any value between if it's a return, right, from minus maybe 100 to plus infinity. The discrete random variables are the variables such as number of days in a year when stock went up. All right, so we have 252 days in a year, and maybe some of these days it was going up, the stocks, and some of the days the stocks were going down. So we'll just designate those days when it's going up and when it's going down, and we'll just count those where it was going up. So obviously it can be from 0 to 252. If it's a very bad year, I guess it's 0, right? I don't think we ever had a year where every day the stocks were just going down. It's quite unlikely actually. But although conceptually these two variables were, as I was saying, continuous and discrete, continuous variables in practice, they are how would I say, they are not as cleanly continuous as the theory would suggest. So think of the percentage return as a continuous random variable, and yes, it is continuous, can be any percentage return, but in practice, think of this: money is recorded in discrete precision, let's say in cents. So if your portfolio is in hundreds of thousands of dollars, usually the value of it at the bank or at your brokerage will be recorded at a precision of a cent, right, up to 1 cent. So if you think about this, then there is only a countable or if even finite number of percentage return you can record. Just think about it, because it's not like real number in math, right? This is the number which you record in a computer with 1 cent precision, so it cannot be just truly continuous. So that's the complication which we are going to largely ignore, and rarely these complications are how would I say, are important, right? So we will just assume it's a continuous random variable, but just remember, whenever you're using digital computers, there's nothing truly continuous, right? Everything is recorded and calculated with a finite precision. Now, one important distinction here is that discrete does not imply finite, right? So oftentimes when examples are shown of discrete variables, the examples are of finite sets. So for instance, well, maybe my variable is a day of the week. It's finite, right? It can only be 1 through 7, Monday through Sunday. Or a month, or a day of a month. Okay, it's finite, 1 to 31. So we make it confused, and we tend to get to think that discrete is finite, because all these examples are always finite and finite. But some discrete random variables have infinite number of possible outcomes, right? And we will talk about them in a few slides. So let's think of a probability density for a continuous random variable. So probability density function is well defined for, or not well defined, but I would say is a conventionally looking function for continuous random numbers, and it's actually defined as the probability, right? So the probability that your observed number will be between A and B turns out to be an integral of the of this density function. So you can think of a density as almost like physical density in that regard. It's density of probability. It's probability per unit of your x variable, right? And that's why we can actually define this density as a derivative of our CDF, cumulative distribution function, and conversely our CDF is an integral. So CDF x, f of x, CDF, is equal to an integral from minus infinity to x of the density function. Right, so oftentimes the density function is shown in plots which are similar to what you see on the right side, and then we talk about areas under the curve, right? So we know the meaning of an integral, right, is an area under the curve. So in this case we could say that the probability that the number will be, let's say, between sigma and minus sigma, and this is a normal, standard normal random number, or any random number, any normal random number, right, Gaussian. So in this case we will say the probability that the number will be between sigma and minus sigma would be this integral, right, the first integral. So we have this density function, and the area under the curve under the density function is the probability. So again, probability is a density, PDF is a density of probability. In order to get probability, we have to integrate the density, right? So PDF is not, and I'm going to make it very bold and large, is not the probability of outcome X. It is even not the probability of outcome being in vicinity of X. So I've seen this, I think it was FRM preparation video on internet, in YouTube actually. I forgot who was the provider, but one of the very popular providers of a financial risk management course preparation modules, right? So they were saying that PDF is a probability of x being in vicinity, right, of some number. So like we will say that your x is between x and x plus delta x. So they were saying PDF is that probability. No, absolutely not. It's a huge mistake to make, right? So don't make it. In order to get the probability, we need to get the area under the curve. Correct. So what we do is we could say that the probability that your number is between x and delta x, so in vicinity of x, right? X or a little bit around x, is what? Is the density at x multiplied by delta x. It's very important, right? By by that area. So in order to get the probability, we always need the area. Probability is not defined at one point, and that is the case for continuous numbers. But if we're talking about the discrete random variables, then instead of the PDF, usually we use probability mass function, PMF, and we will see in a few why. But probability mass function is defined as the following: that probability, it's a probability that your observed x is equal to given x, right? So px is equal probability. So in this case, PMF is not the density, right? It is a probability. So I'm showing this simple example from Wikipedia with 3 outcomes. You have the probability distribution with 3 outcomes, 1, 3, and 7. And their probabilities happen to be 20%, 50, and 30. If you add them up, they should add up to 100 to 1. And the same thing actually with PDF, obviously, right? So do I show it here? I didn't show it, but it's sort of it should be obvious, right? Because if we take the we know that f of infinity, the CDF of the infinity, right, is equal to 1. So we can say that the density under, if we integrate this density function from minus infinity to plus infinity, it should add up to 1. So I didn't say it here, but it does, it should. Similarly, with PMF, we don't need to integrate. It's a discrete number. We summate, right? We sum. And when we sum, the sum should be equal to 1. The sum is equal to 1. The probability itself should be greater or equal than 0. It's typo. Let's fix it very quickly, right? Give me a second. We don't like typos. Okay, great, right? So the probability mass function and the density too, actually, should be greater than or equal to 0. But the sum, they should add up to 1. So in this case, when I say add up to 1, you have to run through all the outcomes of random variable. Again, similar to PDF and in PMF, we have to run across all the outcomes, right? These are not observations, these are outcomes, possible outcomes. PDF, we can also define PDF for discrete function, although, as I said, we normally use PMF, but you can define PDF. The problem, though, that it requires this generalized function called delta, and I wrote it this way. I will not use delta function in my course, but it's something very handy, something you better know, right? It's not strictly required for this course. It's a generalized function. It's not your usual function. It's a very interesting kind of a mathematical object. So I just mentioned it, and let's move on, right? Now that I wanted to point to this very interesting paradox, and for those who do not have advanced calculus knowledge, it's good to know about this paradox without getting in details. But think of this: unlike discrete random variables, for continuous random variables, probability of any concrete value for continuous random variables, probability of any concrete value is 0. So let's take a look at it. We said the probability that our random observation is in the vicinity of x, right? So between x and x plus delta x. We said is approximately equal to the density at x multiplied by the width of the region, right, delta x. But imagine we want to be more precise, right? We want to get the number actually right at x. We don't want a region, so we will decrease this delta x to, let's say, to 0. So if delta x collapses to 0, what happens? Your probability becomes 0. Think of the area under the curve, right? So when our delta x is smaller and smaller, area is smaller and smaller too. So you see the density around any point is not 0, right? It's not 0, but area, when we're squeezing this area, we're getting like a narrower and narrower region. The area under the curve, under the density, is becoming smaller and smaller, although the density itself is not. So eventually, if we collapse delta x to 0, probability of x being exactly equal to any given number is 0. So probability of observing any concrete given number of a continuous random variable is equal to 0. Now there's something interesting, right? Okay, if we know the probability is 0, then we have the situation where we're basically summing 0. So let's say we want to calculate we want to calculate all the probabilities, add up, right? So if we're integrating, adding up all the probabilities of each number, each probability is 0, and somehow we add all these 0 and still get 1. How is it possible, right? Because if we have two zeros and add, it's still 0. You add third 0, it's still 0. You can keep adding those zeros and it will always be 0. But somehow, in random variable case, sum of zeros is equal to 1. I do not think I can explain it easily here without some measure theory apparatus, right? Some calculus. So I'm going to just refer you to it. So if you're curious about it, you should definitely know about this sort of a paradox that it happens. Probability of any random variable, such as normal, right? You take any normal number, like let's say 0 at the peak of the standard normal variable's density. What is the probability that you will observe exactly 0, right, of the standard normal? And I'm going to tell you 0. I repeated it already like 20 times, right? So it's interesting. It's exactly 0. And then we're adding them all up, and somehow it's not 0. So what's happening here? This is what's happening. It's something called, it's related to a concept called power of continuum in calculus. But the idea here is the following. So you just need to understand the concept. You don't need to understand the exact mechanics. So the concept goes like this. So discrete random variables, their outcomes, all right, they're mapped to finite or infinite but countable outcome sets. So for instance, if you have a coin toss, it's 0 or 1, right? So it's finite at 0 or 1. But if you have something like Poisson distribution, you can have infinite number, right? 0, 1, 2, 3, and to infinite number, any natural number. So it is an infinite set, 0 to all the other integers, non-negative integers. However, it is a countable set, and when we say countable, we mean that if your set can be mapped to integer numbers such as 0, 1, 2, 3, if you can enumerate them. So if you can enumerate them, then they're countable. And what happens is that if you are adding zeros and in a countable way, countable set of zeros, then the sum will always be 0. But when we have the real numbers, so let's say you have continuous random variables such as normal, then the set of all possible values which normal distribution can produce is not only infinite, but it's also not countable. and that's when things get interesting. So if you are adding zeros of non-countable set, then the sum doesn't need to be zero. So with countable sets like integers and distributions such as Poisson or any discrete distribution, sum of zeros will always be equal to zero. But with not countable sets such as random variables of normal distribution, right? The sum of zeros does not necessarily add up to zero. It can be greater than zero or lesser. Now, the final couple of points are about the units of measure. It's an interesting subject, right? So those who come from physics, let's say, or engineering, we're always acutely aware of units of measure. Somehow people in other fields, they pay less attention, but in physics for engineering, units of measure analysis itself can be very informative. So I'm going to mention what are the units of measure, meaning the output of the functions such as CDF or PDF. What is the units of measure? So the domain of arguments of all three functions is real numbers. It's all real numbers from minus infinity to plus. Even for discrete numbers, the inputs are from minus infinity to plus infinity, except if you're plugging, let's say, minus infinity into something like Bernoulli distribution, it will always be 0, 0, 0, and only at the values of chosen values 0 and 1, it will have non-zero values. So the inputs into CDF, PDF, and PMF are all real numbers, and the unit of measure is whatever the unit of measure of your random variable. So for instance, if you are studying distribution of portfolio value tomorrow, then it must be dollars. So the input into CDF, PMF, or PDF will be dollars. Now the outputs are interesting, right? CDF and cumulative distribution function and probability mass function outputs are in the units of probability, and I already mentioned it. I said PMF is the probability and CDF is the probability. So whatever the units of measure probability you are using, for instance percentage, like 70% or whatever, that is the units of measure. Or if you're using decimals, it would be 0.7. Right, the probability, which corresponds to 70%. PDF output, though, is in the units of probability per unit of measure of the variable. Again, if you are looking at the PDF probability density function of, let's say, your portfolio value distribution, then the output of PDF will be in what minutes? It will be in units of measure of probability per, let's say, dollar, right, per unit of measure of your argument variable. Now, again, remember, PDF is not the probability, it's a probability per unit of your random variable. Now, let's emphasize the distinction between outcomes and observations, right? Never mix up outcomes and observations. So, for example, we have a single coin toss, and what is the outcome? It's going to be 0 or 1, or heads and tails, right? Let's say heads and tails are mapped to 0 and 1. Then the outcomes, the set of all possible outcomes, is just two numbers, 0 and 1. That is the only outcomes which can be generated from a single coin toss variable. However, we can collect any number of observations, so we can keep tossing the coin and recording the outcome. So for instance, we tossed it 1,000 times, and then we were recording the outcome 0, 1, 1, 1, 0, and so on. Right? So the outcomes are 0 and 1, just two numbers, possible outcomes. But the observations can be any number you observe, right? Finally, let's look at the function called inverse CDF, or also quantile function. CDF, cumulative distribution function, has an inverse. Inverse meaning, so when we're plugging the random variable, or like any number, into CDF, it returns us the probability between 0 and 1. So the inverse function will accept the probability, meaning inverse function will accept the number between 0 and 1. So if we provide the number between 0 and 1 into the inverse CDF, which is usually denoted with f power minus 1, right, like an inverse. So if you plug the probability, or a number between 0 and 1, for that matter, any number between 0 and 1, you will get a value x itself. You will get the random variable back. Right? So it accepts numbers between 0 and 1 and returns corresponding random variable. So for inverse CDF in software such as Excel, for instance, we have functions such as norm as inv, or in Python, let's say we have this pdf function. Inverse PDF is rarely well defined, right? Because we can define inverse because it's a monotonic function, monotonic increasing function, but PDF is not monotonic, right? It can go up and down and so on. Usually it's not monotonic. There are cases where it is, but most of our PDFs are not monotonic. So defining inverse PDF is a little bit tricky, right? Because of the mathematics. It's just not that as easy, right? So I want to show you an example of using inverse PDF here, right? Let's see. So let us say we want to find out the probability, maybe 0.75 of what would be the standard random normal with probability 0.75. Let's see. The number, as I said, the function is norm standard inverse, and let's plug the number 0.75. So we're going to get some number, 0.67 or something like that, right? So why don't we just take the same number and plug it into a CDF. So this was inverse CDF. And now let's get the CDF itself. The number, initial number was x. Let me take this. Maybe I'll align it like this. Okay, good. Now let's just check it. Let's get a CDF of this number, right? So this was this was probability. We plugged 0.75. Supposedly we got inverse CDF. Now if we take this number 0.67 and plug it into CDF, we should get back the probability. Let's say if it works or not. Of course it works, but I just want to show you how it's done. So we need to use norm. Well, we need to use standard normal distribution, right? And we will use the output of inverse CDF, but then we need to tell it that it's a cumulative, because the same function norm as dist can produce you the CDF or PDF. So if we say true here, it's CDF 0.75, right? So we proved something here. Right. By the way, what if we want to get the PDF of this point? Let's see. So it would be exactly the same function actually, but instead of true, we will say false, and that would mean it's a PDF. So let's say false. You see, so PDF is 0.31, and as we said, 0.31 is the density, right? It's not the probability. Now let's look at something interesting. Let's test this theory with Excel, as if we could test a theory with Excel. So remember here, right? Probability density function. I said probability that the number is in the vicinity of delta x, all right, is equal to what? Density multiplied by the size of the region. So let me increase this a little bit. Let's choose x, some x, and maybe the x would be 0.5. It's pretty much random, right? And then let's choose a little region here, so maybe the width would be 0.1. Now let's calculate the CDF, right? CDF at x, and this would be norm. We're using standard normal distribution, and this would be CDF of the number x, and we will say true. Now let's get the CDF of x plus delta x, right? This is going to be f2 plus f1. Okay, good. And now we can calculate the exact probability. And we know the exact probability is going to be CDF x plus dx minus CDF of x. Great. Now let's calculate the PDF at point x. And this is the function which we already looked at, right? But we are going to say false here instead of true. So this is a PDF, meaning it's a density. You see the probability, and here's the density. We'll check a couple of things actually here. So why don't we calculate approximate density? So how do we do approximate density? Well, we can take this probability and define by the width of the area, right? So here's our probability. We'll divide it by dx, and the number is what? 0.34. Now look at the exact PDF. So it's somewhat similar, not exact, but it's close, right? Now let's calculate approximate probability. That is, according to this formula, density multiplied by the width of the area. So our exact density is here, and we will multiply it by dx. Right, again, so we are comparing 0.0352 to exact probability 0.34. So it's close, but it's not exact, right? So why don't we now estimate the error, right? So the error is going to be the true value of approximate density, right, minus the density we calculated, and then okay, wait a second, what did we do here? We said we need to get the true density of this, right, and subtract approximate density. So this is our error of the density, and here's going to be an error of the probability. So we take the true probability and subtract approximate. So the errors are not that large, right? We see, well, how can we decrease the error? Well, we can narrow down the region. So instead of using 0.1, why don't we use 0.01? So we will get a 10 times smaller region. And all of a sudden, look, the approximate probability just is collapsing. It's becoming very small. So if we keep decreasing the area, not the area, but the width of the region, we get narrower and narrower. We get smaller and smaller error, right? So our approximation seems to be working, but also working is what? Also working is this problem. Power of continuum, right? So if we keep squeezing this region, what is going to happen? The probability will be smaller and smaller. How can we see it? So let's plug a really small number here. Maybe 1 minus 9. 1 minus 9, it's like a 1 billionth, right? 1 out of a billion. If we plug this number here, we see what's going on with probability. It's becoming very small. Right, so while we're so what will happen is, like, if we plug 0 here, obviously the probability will become 0. So all the other numbers get messed up, but the probability is 0, right? So this is not a mathematical proof, but you get an idea. So I'm just illustrating you how this power of continuum works, right? How, because of the power of continuum, how we are adding zeros and somehow the sum of zeros is not zero. So on this, we are going to finish this chapter.